here are your vocabulary words for chapter 4. This is chapter 4. And here are your vocabulary words. Now, we're going to go through the anatomy of a wave. We're going to do the first 2 pages today. And this is the anatomy of a wave. This is the electromagnetic spectrum wave. And most of this you should have covered in middle school. So this should be mostly a review. So we're going to go through it pretty quickly. All right. So we're going to start with energy and light travels in waves. And this is a transverse wave. And a transverse wave carries light. So it travels through the molecules like this, and it pushes the molecules aside as it travels through them. All right, now, does anybody know the other type of wave? So the other kind of wave is called a compressional wave. Compression wave. And it carries sound. And the compression wave looks like this. It is a spring. And it's open, and then it gets closer and closer and closer and closer and closer, and then it opens back up again, right? That's a very bad drawing, but you kind of get my thing. So, right? And it has a wavelength that looks like this. So the wavelength is where it's really widely open, and then where it's closed up again, and then where it's open again, all right? And so this is one wavelength that I've bracketed off here, okay? And the transverse wave has one wavelength right here. This is one wavelength going from one point on the wave to another point on the wave. So what we want to do is we want to next go through and do the, we're going to talk more about sound waves, but in case the, so we're going to go through the anatomy of the wave here. So the A is for amplitude, and that is the distance from the rest position to the top of the trough, which is T, the bottom of the trough, which is the T, or the top of the crest, which is the highest point of the wave. All of that should have been basically review. And then the wavelength is the distance covering the entire wave from one point on the wave to the other identical point on a later wave. So wavelength is very important, and so we have a special symbol that we use. It's called a lambda. It's a Greek symbol, lambda, and it's spelled L-A-M-B-D-A, lambda. So lambda represents the wavelength, and we're going to be using that quite a bit in this portion of the unit, all right? Now, how much of this do you need to know? Well, because you have the wave quiz coming up, you need to know all of this for the quiz. Can't be much clearer, right? Okay, anatomy of a wave. All right. Okay, turning the page. So frequency of a wave. So now we've done wavelength. So now we want to talk about frequency of a wave. So frequency of a wave is the number of cycles. So actually frequency could be the number of taps per second. The number of anything per second is the frequency, right? But for us, we're looking at waves, and it's defined as mu. That's the Greek letter we use, and we draw it like this. It's like a little U with a little branch coming off of it, okay? And the units that we use for frequency are called hertz. And they are abbreviated as Hz, or 1/2, because we say waves per second. So this is per second. That's the unit. Whatever it is per second, right? Heartbeats per second. That's the frequency of the heartbeats, okay? Whatever it is per second. Or you could do this, seconds to the -1. And that, mathematically, anything to the -1 is 1 over that thing. So this, 1/s, and s to the -1 are ultimately the same thing mathematically, right? Okay. Now, wavelength and frequency have an inverse relationship. And what that means is that wavelength increases as frequency decreases. So if we put this in using our newly learned symbols, we would have as wavelength increases, frequency decreases. And those are the symbols that we just learned. Like the train cars, as I'm standing on the side of the road, counting the train cars that are passing on the train, if the train car's length were to decrease by half, the number of train cars I would see would increase by a factor of 2. So as wavelength decreases, so as the length decreases, the number of cars I see increases. Okay? So as the length of the wave increases, I see less waves. And actually, this is directly proportional. If I double the wavelength, I see half the frequency, half the waves. Okay? All right, now let's talk about the electromagnetic spectrum, which I believe that you've covered 100% in middle school. So the electromagnetic spectrum is transverse waves, and it includes all the ones that you guys mentioned before. So we start talking about radio waves. Now, radio waves down here, they have a very long wavelength. How long? Well, it's actually the length of like 3 soccer fields. So radio waves, AM radio waves, are the length of 3 soccer fields, 1,000 meters long. And they go all the way up to gamma rays. Yeah, gamma rays. We know what gamma rays are. Look at that, man. Gamma rays. And gamma rays have a very, very short wavelength. How short? Gamma rays have a wavelength that is not the size of an atom. It is 10,000 times smaller than that. It is the size of an atomic nucleus. The gamma ray's wavelength is the same length as the diameter of an atomic nucleus. That's how small they are. So when we talk about the frequency of the radio waves, we're talking about Being very low, at 10,000 waves per second, they're moving rapidly, aren't they? To very high, at 10 to the 20th passing you per second. Some of these in between are microwaves that are the size of a honeybee, and ultraviolet waves, which are the size of a molecule. Okay? So there's a great range in here, right? Visible light, which is not damaging to you, is right in the middle. Visible light. We're going to talk a little bit about visible light. Now, what do you need to know about this electromagnetic spectrum for your quiz and your knowledge? You need to know the relative sizes. So how do we know that? What does that mean? So what that means is I would, if I was putting this on my periodic table, I would put the smallest wavelength and then the largest frequency, and then I would line them all up because that's all you need to know. You need to know comparatively which one has the larger wavelength, microwaves or X-rays. Which one has the lower frequency, ultraviolet or radio waves. So you would want to put these in order so that you can look at your scale and see relative to the other ones which ones are where. You do not need to know numbers. You just need to know which ones go where, so that relative to each other, which one has larger or smaller of what, okay? All right, moving on. Lastly, on the notes for today, visible light. So, visible light is in the middle. Of the electromagnetic spectrum. And we have a way of remembering the visible light. We can remember it by Roy G. Biv. I believe that indigo is a myth, like unicorns. So red, orange, yellow, green, blue, and violet. I don't think indigo exists. It's not a real color. Indigo is the eye. It's like deep, dark blue heading to purple. It doesn't exist. Red has the longest wavelength and the lowest frequency. And infrared is before red. So if we go up here, you can see here's infrared, then would be red, right? The longest wavelength. Infrared, then red, right? Okay? And it's experienced as heat. That's why your burgers are sitting underneath hot red lights to keep them hot. And that's why when burners heat up on an electric stove, they are red. Yes? Okay, next we have violet, which is the shortest wavelength and the highest frequency. So after violet, you see we have infrared, then we have red, orange, yellow, green, blue, violet, and then we have ultraviolet. So after that, we have ultraviolet. And ultraviolet is after violet. Which is before X-ray, which as we know is not good for you. X-ray, right? Not good for you. And this is not good for your skin. Oh, UVB. ultraviolet beta, because the end of the ultraviolet spectrum is the bad cancerous rays. Okay, at the end of the ultraviolet spectrum toward the X-rays, up in here. That's why you don't want to be around ultraviolet light for too long, because some of it's fine toward the violet color, but then up toward the X-ray, not so good. Okay?